polar molecules. Now we're not talking about molecules that are cold. Okay. Okay. What is poles? Poles. Now, she said opposite ends. Does that sound right? Okay, places you see poles. You see poles on globes, right? North and south. Magnets, north and south. Batteries, plus and minus. Okay, opposite ends. So we're going to talk about molecules. Our goal is to talk about molecules with ends and how they interact with each other. So, and what those ends are going to be like is they're going to be partially positive and partially negative. That's what the ends are going to be. Partially positive, partially negative. Okay? And if a molecule is going to be polar, it has to meet two conditions. In order to have a partially positive end and a partially negative end, it's got to meet two conditions. First of all, it's got to have polar bonds. And we're going to be able to tell that from differences in electronegativity. And so that difference in electronegativity is going to be a minus end and a positive end, because difference in electronegativity means the electrons pull different amounts. If the electrons pulled more this way is going to be a little bit more negative, leaving that end a little bit more positive. Okay? Second thing is, so that gives us the charges. The second thing is it has to have ends. And the opposite of polar is symmetrical. So if the molecule is symmetrical, it won't have ends, because things that are symmetrical don't have ends. Symmetrical means everything's spread evenly around. Polar means one side's negative, the other side's positive. Those two can't exist together. If everything's spread evenly, it can't have a positive and negative end. Okay? So that means I need to look at the shape. So the reason why we learned shape was so we could see whether the molecule is going to be polar. Because if it's polar, it behaves differently than if it's not polar. So, first one, the easy part, figuring out if it's got polar bonds. Okay. If they're shared equally, it's nonpolar. The atoms in a bond are shared equally, then it's not polar. Okay. But, so if the atoms are the same, electrons are going to be shared. But the atoms are different. So O2 has got to be nonpolar because O is going to share with O. But O hooked with N may not be shared evenly. One of them may want the electrons more than the other. It was on. Okay, so that's going to be the polar bond. Okay. So we had a name for how strong atoms pull on their neighbors' electrons. That was electronegativity. Electronegativity is how hard you pulled on your neighbor's electrons. Okay. But it's not how much the electronegativity is, it's how big the difference in electronegativity is. Remember, my analogy for electronegativity was greedy. Okay? And if I put two greedy people on an island, desert island, they're going to share everything perfectly. Because if they're equally greedy, one won't let the other one get ahead. If I give two perfectly sharing people on an island, everything will be divided evenly. Because they're going to, I would never have any extra. I'd give that to the other person. So the sharing's even as long as they're both greedy or they're both not sharing. The sharing's even if they're both high electronegativity or they're both low electronegativity. But if you put a greedy person on an island with a sharer, they're not going to be shared evenly. Because the sharer will say, here, take this. And the greedy person said, I would love to. Okay? So it's the difference in electronegativity. So use figure 520 on page 151. And all that was simply a table of electronegativities. We learned the trends in electronegativity. We learned that the lowest electronegativities were at the bottom, higher at the top because there's less shielding. And we learned that the right side of the table has higher electronegativities because of more nuclear charge. And the most electronegative was fluorine. And that's at 4.0. And then next comes 3.5 at oxygen, then nitrogen 3.0, chlorine 3.0, carbon 2.5, sulfur 2.5. Metals are really low. Non-metals are really high. Okay. And you need the difference between the two. So if the difference is between 0 and 0.4, we call that a non-polar bond. 0 to 0.4. Their electronegativities are close enough together that they're going to share pretty evenly. They're about equally greedy. Now I'm going to draw lines in a different place than your book does. Okay. Your book stops, I think that stops at 1.7. Now I'm going to go all the way to 2.0. Okay. 0.5 to 1 is a little bit polar. 1 to 2 is really polar. So I put those two down there. Both of those are polar, but the bigger the difference, the more polar it is. So that's why I put both of those there. A little bit polar, a lot polar. But let's think about what really polar means. Really polar means that one atom grabbed the other one's electron and pulled it right towards itself, and the other one did not pull back. What happens when one atom grabs another, and if you reach over and grab something, the other person doesn't pull it back? You take it away. And when we take an electron away, we don't call it covalent anymore. We call it ionic. Oh, how do you? Oh, didn't think I heard anything. Hey. Hey. So, no, now I hear it. Didn't see anybody. Yeah, you do it. There we go. All right, so completely evenly sharing, uneven sharing, I've taken it away. Okay? So polar's in the middle. Okay? To show it's polar, we have two ways of doing it. One is to label that partial charge. I can't just put a plus and a minus because that would assume that they were completely positive and completely negative. So the Greek letter delta means partially. That's a lowercase delta. Looks like a S that came up and got its own tail. Come on, one of these has to work. There we go. So I make an S and then bring the tail up. Eventually they straightened it out and it became RD. But so bring that tail up. And that's partial, so delta means partially positive, and delta minus means partially negative. So I've labeled HCl this way, with a delta plus and a delta minus. That's one way to label them. How did I know which one was positive and which one was negative? Okay. Electronegativity. Let's go back to that table. H was 2.1. Cl was 3.5? 3.0. 2.1 minus 3.0, the absolute value of that is 0.9, right? So that's why it's polar, because 0.9 is between 0.5 and 2. Right? Anything between 0.5 and 2 is polar. Okay? Okay, so that's why I know it's polar. How did I know it was negative? Which one was negative? Well, Cl had the bigger electronegativity. It pulled the electron towards itself. Okay? And that's what the second way is showing. The second way is showing that the electrons got pulled towards the chlorine, leaving that end positive. Shows which way the electrons got pulled that way and left that end positive. Make sense? So two ways of showing the same thing. You can either label it with delta plus, delta minus, or you can use the arrow with the plus sign on the one. So we know that Cl minus pulls harder than the electrons, or we can say the electrons spend more time near the Cl. Well, everyone will look at it, that Cl is going to have more electron density. Okay, so that's how you check condition 1 for a polar molecule. Condition 1, it had to have polar bonds. Condition 2, the molecule couldn't be symmetrical. So what is symmetrical? Well, the symmetrical shapes are the ones without lone pair. Because the lone pair pushes those atoms closer together, which means they're not evenly spread around anymore. Because you've got one area where it's lone pair, the other area where it's atoms. Tetrahedral, trigonal planar, and linear. Okay, another way of looking at it. Look at those symmetrical shapes. Where is the atom everything's connected to here? Right smack dab in the middle, right? Linear, where's the atom everything's connected to? Smack dab in the middle. Tetrahedral. Everything's connected to the atom straight in the middle. What about trigonal pyramidal? Is everything connected to the one right in the middle? No, because that one to connect to, they all push down, right? So they're all connected to the one on the top. Okay, and bent. Okay, so the ones where they're all connected to the one in the middle, that's a symmetrical shape. Everything's evenly spread around. Trigonal pyramidal and bent, they're not evenly spread around. They're not symmetrical. Okay? Now, the symmetrical shapes are going to be nonpolar if all the atoms on the ends are the same. So we've talked about CO2 a million times. Throughout this chapter. Well, oxygen's electronegativity was second highest at 3.5. Carbon was 2.1. Okay, this is really a linear shape. So the electrons are pulled towards the oxygens. So the oxygens are negative and the carbon's positive. Does this have two different ends? Oh, it's got two negative ends. So that's symmetrical, that's nonpolar, because you got to have different ends. So if the ends are the same, it's nonpolar. See how symmetry stops it from being polar. It's got the charged pieces, but the symmetry stops it from being polar. It's the polar bonds that make it polar, symmetry can stop it. Okay? So the shapes with lone pair on the atom are not symmetrical. And they can be polar even with the same atoms. If it was linear, we just said that was nonpolar. The symmetry cancels it out. But I take those same three atoms, and instead of having them in a line, they're bent. Now, the electrons are pulled towards this end and this end, and we could say that the bottom is negative and the top is positive. Those two ends are different. The bottom and the top are different from each other. This is a polar molecule. So see how bending makes it polar. Allows those polar bonds to have different ends. So linear, nonpolar, bent, polar. Okay? So let's try a few. HF, is it polar? So I'd have to turn to page 151 and look up some numbers. H was 2.1. H is 2.1. F is 4.0. So step one, does this have polar bonds? Yes, so it's worth drawing. And it's pretty easy to draw because H wants to make one bond, F wants to make one bond. Okay. And the electrons are being pulled towards the fluorine. F is partially negative, H is partially positive. Right on the border, because that difference is 1.9. At 2.0, we would have called it ionic. Right? So really negative and really positive. Does this have two different ends? So is it polar? Yes. Yes, it's polar because it's got a negative end and a positive end. So first I do the simple stuff of subtracting, and then I do the complex stuff of seeing what shape it is. Because if I do the subtracting, and the numbers aren't big enough different, there's no reason to talk about shape. So H2O, H was 2.1, O was 3.5. That's a difference of 1.4. That's greater than 0.5. Right? So it's got polar bonds. H is hooked to O, is hooked to H. There's the structural formula for water. The oxygen, so the electrons are pulled towards the oxygen, so it's negative, and the H's are positive. Is it polar? We don't know yet because we don't know what shape it is. Because it doesn't, it's not, we haven't, that's not necessarily that shape. So I got two atoms, two lone pairs, so two atoms has definitely got to be either bent or linear. And it's got lone pairs, so it's going to be bent. So H hooked to O, hooked to H. The electrons are pulled up towards the oxygen, leaving those hydrogens positive. So the top is negative, the bottom's positive. It's polar. That's polar. What about NH3? Ammonia. Well, ammonia's electronegativity, nitrogen's electronegativity, I looked up, and it was 3.0. So does it have polar bonds? Well, the N is going to have to be hooked to the H's, right? Okay, does it have polar bonds? The difference is 3.0 minus 2.2, that gives me 0.5, but 0.5 is just enough to make it polar. Oh, I'm sorry. It's 2.1, isn't it? It's 0.9, plenty polar. And so now that I've got that these are polar bonds, that the H's are positive because they've got the smaller number, the nitrogen's negative because it's got the bigger number, I just have to decide where they really are. What shape is this? Well, it's a triangle because it's got three H's, but it's going to be pointy because of the lone pair. So it's really the top is negative, the bottoms are all positive. Is it polar? Yeah. That's why it dissolves. That's why it can hang on to water. CCl4. Well, carbon is 2.0 or 2.1? 2.5. Carbon's 2.5. Cl is 3.0. That's 0.5. 0.5 difference, barely enough, but it makes it polar. So then I got to think about, it's got polar bonds. But what shape is it really? Tetrahedral, and tetrahedral is symmetrical, right? Yeah, so all the Cl's are negative. Negative, not positive, sorry. All the Cl's are negative. And the carbon is positive. So we can either say the Cl's are all on the outside, the negatives are all on the outside, or we can say the positive is in the middle, exactly in the middle. That tells me I don't have a positive and negative end. So even though this has polar bonds, it's not polar. We did CO2 on the board already. What about CH3Cl? Well, then I actually have to see what's bonded to each other. Well, carbon was 2.5, H was 2.1, Cl was 3.0. So the carbon makes 4 bonds. I could hook on the 3 hydrogens and then hook on the chlorine. So the types of bonds I have to worry about are the CH bonds, and the CH bonds are nonpolar. That's a difference of 0.4. The Cl bond is polar, 0.5, right? So the Cl is a little bit negative, and the carbon is a little bit positive. Now, it doesn't even matter what the three-dimensional shape is. Is there a positive and negative end to this? Is there anything canceling out that negative? Nothing's canceling out the negative, is it? So since nothing's canceling out the negative, that means that end is negative. Anything canceling out that positive? Nope, that end is positive. So our tetrahedral would have a dipole in that axis. Well, it doesn't really matter. We just turn it 109 degrees. Right? I mean, I could have, if I put the CL over here, it would have been going that way. Make sense? And it's not being canceled out any other direction. So here's how they really tell. We said HF was polar. Normally HF is randomly arranged, but if you put a charge in, they'll line up. In fact, this is how the screens on your calculators work. The molecules are long molecules, and normally they're randomly arranged to get the gray in between them. But to turn it on, they line up charges, they all line up. When they all line up, they block the light. And that's why you see a little black space there. And then you turn off the power and they go random again. And it looks gray. Line up, they're black. Unaligned, it's gray. So, that's how you make polar molecules, which leads to intermolecular forces. Inter, between. So intermolecular, between molecules, from one molecule to the next molecule. So this is what keeps water liquid. Keeps sugar solid. So it's how one molecule attracts another molecule. So without those, there wouldn't be solid or liquid molecular compounds. Okay. Okay, there's two kinds. There's the weakest forces. There's two kinds of the really weak forces. The really weak forces are called van der Waals forces. Van is like count of. Like van der is count of, and Waals is a region in Holland, the Netherlands. Count of Waals. Dispersion forces and dipole interactions. These are the weaker of the forces. One of these is easy to explain. The other one, I got some explaining to do. So I got two kinds of weak forces, two kinds of van der Waals forces, dispersion forces, and dipole interactions. Easy one to explain. Dipole interactions. Di, two poles. Two poles interact. Polar molecules are going to be attracted to each other. Why? Well, we got a negative next to a positive. That's why. We got charges to hang on with. So the partial positive on one molecule is attracted to the partial negative on the molecule next to it. Seem reasonable? Positive on one, negative on the other. So two HF molecules would be attracted to each other. So in a liquid, got positives and negatives attracted to each other, and they're all attracted all throughout. So this is a fraction of a second. A fraction of a second in the life of a liquid. And that's what you have to overcome when you boil water, is those partial charges attracting, which is why water melts and boils at a lower temperature than salt. Because for salt, you have to tear apart full charges. Here, we only have to tear apart partial charges. Partial charges are going to be easier to tear apart than full charges. Okay? So polar molecules stick to each other better than nonpolar molecules. Polar molecules have higher boiling points than nonpolar molecules. Okay, so that was the easy one to explain. Now for the hard one. Dispersion forces. Okay, we got an electron cloud, right? Got an electron cloud. The electrons are in where you have a chance of finding the electron. Are the electrons sitting still? No, they're moving. And they're moving randomly, right? But if they're moving randomly, for one fraction of a second, one end of the atom is, one end of the molecule is going to have more electrons than the other end of the molecule, just because of random motion. That seemed plausible. So one has a partial positive charge for just a second. One in partial positive, one partial negative. So I've got a temporary partial charge. They have a momentary dipole. So what? Because so what if I got one end that's negative? There's the molecule next to it is going to be neutral, so it's not going to stick. Actually, what happens is that the molecule, the one molecule, affects the molecule next to it. It affects the electrons in the molecule next to it. This is called an induced dipole. How the heck can one molecule affect next to it? Let me show you. I know most of you probably have seen this trick before. Does this balloon have a charge? I just blew it up. Does the wall have a charge? No. Does the balloon stick to the wall? No. But by rubbing my hair on the balloon, I'm rubbing electrons onto the balloon and off of my hair. And now they have an opposite charge. Now, does the balloon have a charge? Does it have a charge? My hair moving back? I can feel it moving, so it's got to be doing something. Okay. My hair's moving back and forth, right? So the balloon has a charge. Does the wall have a charge? No. It's too slippery. Balloon sticks to the wall. How come? Well, let's show you what's going on. Rather than the top of my head, they used a wool sweater. And when you rub the balloon, it picks the electrons up off your wool sweater. Wool is just hair from a sheep instead of the top of my head. Okay? Now, you'd see the wall is neutral. But as I move the balloon next to it, there's a whole bunch of negative charge on the balloon. So all the negative charges in the wall move out of the way because they don't want to be next to that. And look what I got next to each other. I got a negative balloon right next to a positive wall, and it sticks. So this is the induced dipole. The balloon doesn't actually move the electrons. Conduct means the electrons actually move. Induct means they get pushed around, but they don't actually leave. Right next to the balloon, it has a positive charge, and the balloon is negative, so they stick. So that's what they mean by an induced dipole. When I bring a negative here, it pushes the negatives out here and leaves a positive behind, because the positives can't move around, because they're big nuclei. Well, the same thing is happening inside from one molecule to the next. So the molecule, so I get a temporary partial charge. It affects the electrons in the molecule next to it, pushing their electrons out of the way or pulling them towards it. So they're going to be momentarily attracted. And then a moment later, everything's going to go back to neutral. So I got two hydrogen molecules, H2s. And for a fraction of a second, this one gets unbalanced. The electrons tend to move this way just randomly. On this molecule, its electrons don't want to be near that negative charge. So it's going to get an induced charge that moves its electrons away. And now we got negative next to positive, so they stick to each other. The only thing it depends on is how many electrons you have. The more electrons, the better they can move around. So big molecules do this better. Bigger molecules have more electrons stick better. And not just the valence electrons, all the electrons. Yeah, Peter. I blew it up with air. Yeah. Oh yeah, it would keep it from floating up. The problem is this wall is too slippery. The surfaces are really slippery. If I put it on the brick wall, it would stay. It just slid down the wall because of gravity, but it's still stuck to the wall. Because if it wasn't stuck to the wall, it wouldn't stay on that rail, right? Because you wouldn't be able to set the balloon on the rail. Okay, so more electrons, stronger forces. And the outcome of that is actually shown on my periodic table, because my periodic table has the color coded by states of matter. All the halogens come as diatomic molecules. But F2 is a gas. That's what red means. Red means it's a gas. Br2 is a liquid. And I2 is a solid. Because F2 and Cl2 are trying to do that with, F2 is trying to do it with 18 electrons. It's going to be able to do it a little bit. Bromine with 70 electrons is going to be able to do it better, so it's going to stick together better. Iodine with 106 electrons is going to do it even better, so good that you make a solid out of it. So the states of matter are affected by how big the molecules are. Big molecules tend to stick together better. How strong can this get? That's a gecko. That's a piece of glass. It's walking upside down on a piece of glass. Its feet aren't sticky. They're perfectly dry. Because it's actually hanging with its foot has got tiny little hairs. Those tiny little hairs have frayed ends. The ends of those frayed ends are nice and flat, and it is using the dispersion forces between those flat pieces and the glass to hang from. It's not sticky. It's all perfectly dry. It's just what's holding that wall, holding that on. Actually, temporary partial charges from the electrons moving around in its foot are affecting the glass. The glass's electrons are being pushed around, and it hangs there. It can hang with 1 foot. That's how strong this can get. They're actually trying to make tape with this because it won't leave a residue behind. It would stick, be reusable, and never leave a residue behind, which is like trying to put prints on a wall or in a museum, something to hold it in the museum, a museum quality tape that doesn't leave anything behind. That would be pretty important. Okay? Yeah, question, Peter? Any surface, yeah. Okay. The third one is called hydrogen bonding. And hydrogen bonding is when you've got hydrogen attached to nitrogen, oxygen, or fluorine. One of those three. And it is much stronger than the first two we did. That's what we use. That shows up in DNA. I think I have pictures of DNA to show you in just a few minutes. So, in one way, FO and N are very electronegative. So it's a really strong dipole, which would tend to make you think it was strong, stick together well. Okay, but nitrogen and chlorine both have the same electronegativity, 3.0, and nitrogen's on the list. And chlorine's not. It's got to be something else besides that. The other issue is they're small. So that the atoms can get close together and the negative is concentrated, or the charge is concentrated. So nitrogen, oxygen, and fluorine are small atoms so they can get in close. Because if I held the balloon out here, it wouldn't be attracted to the wall. Right? Actually, it almost looks like they partially share the lone pair, because nitrogen, oxygen, and fluorine are also going to have a lone pair. And this is the strongest of the intermolecular forces. Okay, lab tomorrow. We'll see. Can I wait till I dismiss you before you get up and walk out? I'd really appreciate that.